Hello, everyone. My name is Naziha. My fellow group members are Alexis, Brad, and Romario, and our project is the Electronic Speed Controller Size Reduction. The Electronic Speed Controllers, or ESCs, are devices inside remote control devices such as cars, boats, and drones. These ESCs regulate the speed and direction that device is traveling in. Major parts of the ESC consist of a power supply stage, a current sensing circuit, a microcontroller, and an interface that communicates with the flight controller. The Flame 180A HV ESC is the recommended ESC for the U15 KV100 motor. One of the key features of the Flame is that it contains an internal battery eliminator circuit, or BEC. It also contains a protection circuit designed to shut down the device if an abnormal start occurs. If the ESC loses signal, output is cut off. Additionally, overload protection results in the ESC cutting off the output if the peak current approaches 340 amps, which would result in a short circuit. Our objective for this project is to design and build an ESC half the size of the Flame 180A. Here are our project requirements and constraints. We are to have the size, volume, and weight of the Flame 180A HV, drive the U15-2 KV100 brushless DC motor through all torque ranges. Our ESC should also be driven by an operating voltage range of 24 to 60 volts DC. It should also be driven with 660 to 900 nanometer fiber pulse width modulated input signals. And for two stretch goals, one is achieve 97% efficiency and allow the tuning of the ESC via web portal with TCP IP connection. And next is Romani with the product overview.
Thank you, Naziha. ESC will be mainly powered by a 24 to 60 volt battery that is then stepped down by a DC controller for the gate drive and linear regulator for smaller internal components. Input signal will be passed from the flight controller via optical PWM to the speed controller, where the processor interprets into motor speed and then is then carried out using FETs. Since our FETs operate on high voltage and require rapid switching, gate drivers are necessary for fast gate charging and discharging. We were implementing a sensorless design when current from shunt resistors is sent as feedback for the motor control algorithm for further operations. Next slide, please. In general drones, the input signal is transferred via an electrical PWM signal. However, in our EC design, we're tasked with replacing this with the fiber communication. This requirement can be done with implementing a photo transmitter on a flight controller to transmit data via optical fiber and a photo receiver on EC to convert it back into electrical pulses for the microcontroller. Next slide, please. Here's a chart showing two different types of fiber optic receivers. Since our sponsor wanted to be able to receive signals in the 660 to 900 nanometer range, we decided to choose a type that can accept a spectrum instead of a specific wavelength. Although the first choice is larger than the alternative, it does not require an additional electrolytic capacitor and inductor for biasing. However, since this is something that was not originally in the Flame, it only increases the dimensions of our Flame, of our design, as there is no extra space vertically for the control board, as it sits below the inverter board and is adjacent to the outer case, thus requiring an increase in vertical case height. Next slide, please. After opening the Flame, we found out the majority of its size was due to their MOSFET configuration and heatsink. Since the Flame runs high current up to 180 amps, the design uses 3 FETs in parallel for each high and low side to reduce power dissipation and conduction losses. To reduce the size of our EC, we proposed 2 options: either decreasing the number of parallel FETs to 2 per high and low side, or increasing the number of FETs to 4, which each having its size and power dissipation trade-offs, which Brad will further elucidate here. Next slide, please.
All right, thank you, Romario. So in order to understand the operation of the Flame 180, particularly from a thermal standpoint, we had to perform bench testing on it. So for this particular bench test, we had it set up with the LU12 to 120 kV motor without a prop. For this motor, that's a 48 volts input at the high end, and with it set to 100% throttle, it drew an average of approximately 6.5 amps, and we set it to a 10-minute runtime, which was the required length set by our sponsor. And so on the next slide, I'll go over the outcome. the configuration. So the temperature was measured in LabVIEW using the MIDAC with 6 thermocouples, 1 per phase of 3 in parallel, and then 1 thermocouple measuring the ambient temperature. So the ambient temperature averaged about 23 degrees Celsius. The max phase temperature for one of the phases was 63.9 degrees Celsius, but the average between all 6 phases, 3 high and 3 low, was 56.36 degrees Celsius. So using this data, we then made a thermal model, which I'll show in the next slide. So this is the thermal model simulating the bench test in SolidWorks. So we created a design of the Flame 180 with its 3 FETs in parallel, 6.5 amps max current, which came out to 0.11 watts per FET, which included the switching losses, set the ambient temperature to 23 degrees Celsius and an air convection of approximately 3 watts per meter squared K, which is kind of a resting air. We set it to 10 minutes runtime, max throttle, and the maximum temperature on this was 56.6 degrees Celsius, which was very close to the actual measured one, so we knew that our model was accurate. So then on the next slide, what we did is we tested it at 100%. So drawing 171 amps of max current, which came out to 4.27 watts per FET. Everything else we kept the same. And so we use this as our baseline. So the flame at 10-minute runtime of full max throttle exceeded 170 degrees Celsius at approximately 2 minutes. And we use that number as that is the FET maximum temperature for the FETs that we're looking at. Next slide, please. So in trying to reduce the size, one of the options that we looked at was doing 2 FETs in parallel. This at 171 amps gave us 8.77 watts per FET, and everything else being the same, it exceeded 175 degrees Celsius at less than a minute, at approximately 40 seconds even. So we knew that this was not going to work at all. So next slide. So next we did 4 FETs in parallel. So by increasing the amount of FETs in parallel, we reduced the amount of current per FET and then the thermal dissipation per FET. So we did a bench test of 6.5 amps max current, which came out to 0.051 watts per FET with the switching losses, and everything else being the same. It reached a max temperature of 29.05 degrees Celsius, which is significantly less than what the flame did. And then on the next slide, we did 100% throttle, so 171 amps, which came out to 2.38 watts per FET. We used an air convection of like a light breeze at 10 watts per meter squared K, and this reached a max temperature of 130.85 degrees Celsius after 10 minutes, which is less than the 175 degrees Celsius maximum temperature. Next slide. So since we saw how efficient that it was operating with those heat sinks, we also did one thermal simulation without the heat sink to see if we could increase our size reduction. And all things being the same, the final temperature on this was 204.1 degrees Celsius, so higher than the maximum allowable. Next slide. So for our heatsink design, we went with the ATS EXL61300RO, which was the smallest one really available that met our requirements. And so this one was 6 millimeters high, 15 millimeters wide, and it's made of aluminum, which is very thermally efficient. And as you can see on the SolidWorks model on the right, we made some minor modifications to it by cutting the sideways grooves to increase pins. That increases the thermal dissipation for vertical rise, so air coming down from above will dissipate the heat better there. And then the side extrusions had to be removed in order to fit properly on our design. And so next I will pass it back off to Romario.
Thank you, Brad. So after turning the thermal simulations on different FET heatsink configurations, we calculated the maximum size reduction possible based on the flame's construction, which was much less than 50% reduction desired from our sponsor. This led into research of other types of FETs, such as silicon carbide and gallium nitride as an alternative to see if we could reduce the size further to meet original constraints. Although silicon carbide FETs allow for greater operating temperatures up to 200 degrees Celsius and extremely low switching losses, their on-state resistance were 15 to 20 times greater relative to silicon FETs, leading to too greater power dissipation during conduction, where our device's region of operation dominates, eliminating it as a possible alternative. Next slide, please. Moving on to gallium nitride FETs, their main advantages over silicon FETs were their switching capabilities of over 1 megahertz. However, now our application, we only require switching speeds of approximately 20 kilohertz, which silicon FETs are capable of, while also providing higher maximum thermal properties and lower power dissipation, thus also eliminating gallium nitride FETs as a possible alternative and only leaving silicon FETs as a solution. Next slide, please. As such, moving forward the best option was implementing a 4 parallel silicon FET design to drive 4 parallel FETs. Calculations showed that switching times between 200 and 300 nanoseconds. Each gate driver would require roughly half an amp to 0.9 amps of source current. Rather than individual gate drivers with each high and low side, we're opting for half bridge gate drivers, which reduces component count, complexity, and mitigates problems such as shoot-through. The UCC 2721, which provides 4 amp sync and source current, was the only half bridge gate driver that met the requirements of our design that we could find, so it was our only option. Next slide, please. Based on TI's FOC and spin, the sensorless design calls for current feedback from 2 to 3 phases. Only 2 is necessary, but 3 provides greater accuracy and detection of short circuits. We're going with low side current sensing scheme over high side as it allows for low common mode voltage sensing and for its ease of implementation in our design. Next slide, please. For this, we're using the NIA 185 low side current sense amplifier, which had the lowest maximum gain error and offset voltage that we could find, while providing a bandwidth of up to 350 kilohertz and a gain up to 200 volts per volt, allowing us to use resistors in the micro ohms to lower power dissipation in shunt resistors. And now I'll pass on to Alexis.
Thank you, Romario. All right. So in our ESC design, we'll be needing both a buck regulator or controller and linear regulator to power our gate driver and other smaller components on our control board. The buck regulator will be dropping down our 24 to 60 volts per hour requirements to 12 volts. These 12 volts will then be used to power our gate drivers. The linear regulator will then drop down to 12 volts to approximately 3.3 volts to power the microcontroller and other smaller components on the control board. To the left are the current consumption calculations that determine the specifications of the linear regulator as well as the buck controller. Next slide. Using TI's WebBench Power Designer, we created a buck regulator circuit that will be used to power our gate drivers, which will then be connected to our chosen MOSFETs. Specifications for the buck regulator design are as followed. As its base, we'll be using the LM5117 buck controller. Specifications for the input voltage will be 24 to 60 volts DC, output 12 volts at 10 amps. The output current can be adjusted up to 17 amps. However, we'll only require 12 volts at approximately 8 amps with our current circuit configuration with the gate drivers. We'll be leaving 2 amps extra for powering other devices and components as well. From the input voltage range of 24 to 60 volts, simulations demonstrated that the efficiency of the controller yields highest at the lower end of its range, which is about 24 volts. Next slide. So here the top left simulation shows that the output voltages vary in a very small range as the input voltage changes. The bottom left shows that the input current does not affect the output current that will be going into the gate drivers. The two right pictures demonstrate that there is a time delay in the buck controller reaching its final value. However, it is just over 1,000th of a second of a delay. And next, I'll pass it on to Naziha to discuss the ESC design schematics.
These are our circuit schematics for our current sensors, gate drivers, and linear regulator PCB boards. And continuing on the next slide, this is our MOSFET board circuit schematic. And these schematics have been translated to PCB design, which will be covered by Alexis.
All right, thank you, Naziha. So the first board we have here is the MOSFET PCB. The MOSFET board is 4 copper layers thick. The top right picture depicts the top layer of the board. The yellow layer is the first middle layer, the pink is the second middle layer, and the green is the bottom layer. The red, pink, and green layers are all grounded, while the yellow layer, the first middle layer of the board, is a power plane. The power plane came to be after the obstacle of the traces carrying large current began to be an issue in the design of the board as they were increasingly thick. We added the power plane because otherwise the traces would have needed to be much larger, further increasing the overall size of the board. The power plane aided in the current distribution between those devices connected directly to power, such as the MOSFETs. Heat dissipation was also a factor to consider, as a power plane would cause a heat increase higher than that of thicker traces. However, noting our simulations of the ESC case, the aluminum case, we determined that this would not cause issues in our ESC. After designing the board, the final size of the MOSFET board resulted in being about 4.6 inches in length by 2.535 inches in width. Next slide. So size constraint with the board is primarily due to the size of the traces and vias because of the high current that they would be carrying. In addition, blind vias were initially proposed in the design. However, the cost and time for incorporating blind vias, the size we required, some being about 15 mils to 35 mils in hole size, this was just not feasible or practical. This resulted in all the vias of these sizes, 50 and 35 mils, to be converted to through hole. For the motor phase connections, we followed a similar approach to that of the Flame 180A by removing the solder mask from the traces connecting to each phase, as seen by the red arrows on the bottom figure. This was so that we could add solder to these traces, increasing the vertical width and avoiding to make the traces horizontally thicker. Next slide. So for the gate driver board, we combined the gate driver circuit and the current sense amplifier circuit as part of the control board. This was initially designed to function together with the F280049C launchpad, which contains the MCU of our choice for the ESC, C2000 processor, to control the MOSFET board. Pin headers were placed in order to connect this board with the launchpad and to the MOSFET board via jumper cables. This was part of the original plan to verify our circuits' performance and to test the code developed so far. Next slide. Using TI's Code Composer Studio, we had been using InstaSpin FOC labs provided by TI as a basis for our motor control algorithm, as they are open source minus the fast observer, but this is encoded into the InstaSpin solutions, and provide various solutions for motor control design. As of right now, the code generated thus far has only been tested with the C2000 launchpad and the gate driver eval board we have with our current motor to test the motor parameter identification feature of InstaSpin. These motor parameters were then used for speed control of the motor, being able to adjust the speed of the motor using the standard PI speed controller within InstaSpin. As part of our Innovation Day presentation, we also recorded the motor spinning using the developed code. Next slide. So for our final design, our ESC design included a 4 1.2 milliohm FETs in parallel. This configuration reduced power dissipation per FET, and a smaller heatsink would be required. A single 1000 microfarad tantalum capacitor is added as a reduction of the flame's capacitor block. A 6 millimeter thin aluminum heatsink was also designed, as this was the smallest available heatsink to meet thermal requirements. The final FET board resulted in being 4.68 inches by 2.535 inches. Case dimensions were about 121 millimeters by 67 millimeters by 26 millimeters. Our final volume resulted in being about 210,782 millimeters cubed, while the flame's volume was about 200,788 millimeters cubed. Our board resulted in being in a about 5% size increase in comparison to the Flame 180A. Next, I'll pass it back to Naziha.
For our member responsibilities, Alexis covered the motor algorithm, I covered the FETs and PCB design and switching design, Brad covered the thermal casing and motor algorithm, and Romario did the FETs and signal communication. For our project process, we split it up into four major parts, starting with our research phase, going into design phase, implementing that into our build phase and completing final testing. And this completes our presentation. Thank you for your time.